Okay, shall I start?
Yes.
Okay. So let me remind you of where we were before we broke. We deduced that this object here was a random variable that converged to 0. We knew already that mu t converges to 0 almost surely, and we'd made this, quotes, wrong assumption that there was a positive measure of set of states where mu t didn't tend to 0. Okay? And what we can deduce from that is that there's this complementary set of on this same set of states, essentially, we've got to be in the set xt. We've got to be in a world where, from the point of view of the uninformed player, the informed player is playing almost like the commitment type. Okay, but that's only one period. That's only one xt. But now think a bit more about the kind of convergence we've got going on here. We know that with a fudge factor, that mu is going to be away from when we're in this set of states here. We know with this fudge factor that with very, very high probability, mu is going to stay positive. It's not going to converge to 0 if we're almost converged. And so we know that with very, very high probability, we're always going to be in the state x. So we know with very, very high probability that all future periods, it's going to look, from the point of view of the commitment type, like from the point of view of the uninformed player, like the long runs player is playing like the commitment type. That comes from the convergence. Okay? So, there are a couple of issues there, but let's summarize that first of all. Where we're in the red set, we attach very high probability to be an xt in all future periods. Of course, first issue is we may not know we're in the red set. Red set is something that's defined at time infinity, but may not know we're in the red set. But again, we can finesse that by making a kind of uniformity argument and saying, well, with very, very high probability, if we're in this state, we think we're going to stay in the red set. But the most important thing is, once we're in the red set, or think we're in the red set, it looks like, and we're close to having converged, it looks like all we're going to see on into the future forever are commitment type actions. And why is that true? Well, that's got to come from the convergence of beliefs. If I think I'm going to learn something in the future, I think my beliefs are going to move around a lot in the future, then I'm going to be expecting some different behavior at some point in the future. So the fact that I think my beliefs are close to having converged must imply that I think nothing much of any information is going to be gleaned from what I'm going to see in the future. So that's going on in the mind of player 2, the player who's doing the learning. The way I've rigged this example was whatever player 2 knows, player 1 also knows. Because player 1 gets to see the history of actions, they know the beliefs that player 2 started with, and so they can do Bayes' rule, they can do the inference that player 2 is doing. And so if player 2 knows that, or thinks that with very, very high probability, all they're ever going to see is the commitment type in the future, player 1 also knows that they know that. And they think that player 2 is going to be playing the best response to the commitment type with very, very high probability all the future periods, whatever they see. So that's that. And then my final point, which I need to go more slowly over because I keep rushing the final points. My final point is that that's going to be true whether player 1 does top or bottom today. Because under the commitment action, this is going to be a random outcome. And one of the things that includes with very, very high probability in the future is whether I go top or bottom today. So whether I go top or bottom today, I, as player 2, believe I'm going to see the commitment action in the future. With very, very high probability, I, as player 2, believe, as I, as player 1, believe that player 2 is going to be playing a best response to the commitment action with very, very high probability in the future. Okay? So that's the bottom point. So what does that tell us now when you're in player one's mind? Player one, whether they go top or bottom today, player two isn't going to change their behavior very much. With very, very high probability, they're going to be best responding to the commitment type. So there's going to be no punishment to player one going bottom today. Well, there's going to be a very, very small punishment, but nothing substantial. If we go out along that tail, as we get converging and converging and converging, we can make that punishment really, really small because those probabilities are getting really, really small. So this is where our contradiction comes from. Because now player one faces a choice. They can go bottom and get 3 and get a very infinitesimally small change in their continuation payoff, or they can go top and get 2 and get some other continuation payoff. 3, 2, small change in continuations. 3 is going to be better. So 1 can costlessly do 3 or bottom at this point, and this gives us a contradiction. It gives us a contradiction because 1 has now taken a very informative action. 1 took an action which is very different from the commitment action, bottom. And so player 2 ought to learn a lot from watching what player 1 did in the current period. But that's something we just assumed couldn't happen. We assumed we were on, down, and having converged. Right? So it's the fact that things are converging that gives us this contradiction. Okay, so what did we assume on the route? Okay, well, the only thing we assumed was that quote's wrong assumption. Everything else is just martingales, convergence, very, very strong results for what we know. And so that's got to be the thing that's wrong. The thing that's wrong was the assumption that there was this positive measure set of states of the world. A bit fast there. There was this positive measure set of the states of the world under the p tilde measure, such that mu stayed away from 0 on that set of states of the world. It cannot be the case that mu stays away from 0 if the normal type is present. Okay? So there's the last point on this slide, but I actually have just said that. Okay? So what I'm going to do now, I hope, I'm not quite sure what comes next, but what I'm going to do now, I hope, is give you a more formal explanation of the result, and then point to all the holes in this, which I've just, this kind of hand-waving chat that I've just given you to say why the proof that you would actually read somewhere would be much worse than what I've just done. So let's see what's going to happen. Okay, good. So here's the general result. The general result is, let's suppose player 2 has a unique best response to some commitment action alpha hat 1. So this is some uncertainty about player 1's action, and player 2 has got a unique best response to that. Let's suppose that this pair, alpha hat 1, A2, A hat 2, are not a Nash equilibrium. So built into this is player 2's best responding to alpha hat 1. So what's happening here is player 2 is optimizing, but player 1 may not be. So we're saying this is not a Nash equilibrium, so what that means is there's something different that player 1 can do that is better than A hat 1, alpha hat 1, when player 2 does A hat 2. There's a temptation to deviate. This argument won't work if what you're trying to build a reputation for is something perfectly credible. So if you imagine the battle of the sexes game and you're trying to commit to your most preferred outcome in the battle of the sexes game, this result doesn't apply. But in the game, like the product choice game, does apply. So that's what we need for this temptation to make small cheats. Then we're going to have another assumption on the nature of the monitoring. We're going to assume it's public monitoring, it has full support, and it allows players to statistically identify each other. So I'm sure there's lots of econometricians in the audience, but basically what that means is did anyone cover this so far? No. Okay. Why didn't you do it, George? I blame George for everything. Okay, so the distribution of the public signals that you see when I take a particular action is a different distribution from the distribution of the subject signals you see when I take a second action, and there is no linear independence between those distributions. Okay, that's basically what this means. So that's that. So if these three conditions are true, so there's a best response, there's a temptation, there's noisy public monitoring, then it's got to be the case that reputations vanish eventually. They can't last forever. So there's a paradox here, right? It seems like I've already told you reputations are valuable, but here I tell you reputations don't last forever. Well, that's okay. You just get lots of payoffs early on, and then later on you cheat and you get lower payoffs. It's fine. Okay? What about these assumptions? Which of the ones do we really need? Well, we certainly need full support monitoring, because if the distribution of signals you get are different for different actions I take, it might be the case that you see a particular signal only if I deviate. And if you see a particular signal only if I deviate, then that's going to be enough for you to identify my deviations and potentially punish them for me. So this argument won't work if the monitoring structure does not have a common support, I suppose is a better way of putting it. Second question, why do they need to identify each other's actions? So this requires the uninformed player to figure out what the informed player is doing, and at the same time it requires the informed player to figure out what the uninformed player is doing. Why do we need both of those directions? So am I going to do this here or next? I'll do it here, and if it's too late, if you see it again later, we'll pass over that. First reason why we would need the informed player to identify the uninformed player's actions. Well, there was a step back in this proof where I said, this chat. There was a step where I said, whatever the uninformed player knows, the informed player knows too, because their information sets are nested. That's not true in general with perfect monitoring, right? It might not be the case that whatever the uninformed player knows, the informed player knows. But in particular, the informed player may not know the beliefs of the uninformed player. Okay? So how on earth are we going to get this argument going? Because what we really need to know is when the uninformed player's beliefs are settled down, the informed player then gets the ability to exploit that convergence. And so it needs to know when the uninformed player's beliefs are settled down. How is this going to happen? Oh, question.
Isn't it enough for the informed player to observe the signals that the uninformed sees?
No, because of the randomizations that might have occurred.
But if he sees the same signals, then you can say that he knows whatever the second player knows.
No, because the uninformed player, it doesn't directly see the actions. So not necessarily. If there's some mixing going on, not necessarily.
Yes, the uninformed player sees some signals that are a function of the actions of the first.
Mm-hmm. But if there is some randomization in the past, how you interpret these signals is difficult. So anyway, let me continue. Oh yes, we were thinking about the problem of knowing what the uninformed player knows. Well, actually, you may not need to do that, because what we really wanted to know is what the uninformed player was doing. We wanted to know whether the uninformed player had settled down at playing a best response to the commitment action. That was enough for the contradiction to go ahead. So if we can identify when the uninformed player has settled down and now playing a best response to the commitment action, that would be enough. And so that's why we need this. So that's why we need mutual knowledge. It's not enough for the informed player to know about the, uninformed player to know about the informed player. We need the informed player to know about the uninformed player. The other way we need public statistical identification, just in order to build a reputation, you need to be able to identify what the informed player is doing. If you can't see what they're committing to, then of course you can't build a reputation. So that's why those things are necessary. So why was the foolproof so involved? I cheated a lot. First, I ignored lots and lots of issues about convergence and uniformity, which really need a lot of care. So that's something that we glossed over. Second, we only dealt with the very simplest kind of public signals, and that also requires a much more sophisticated kind of argument, the kind of argument that George made this morning that about the kind of you know that I know kind of issues. And third, here it is, what I've just been telling you, that we need to worry about the mutual knowledge of these players in this game. So it's not so bad, it is pretty tricky to show that this convergence drives these players to a subjective equilibrium of the game. But what we're really showing here is something about the objective behavior, our common knowledge about what each other are doing, and we're kind of using that to exploit that to get a contradiction. And to get this common knowledge of a potential deviation is much harder. So that's why when you read other proofs of this, well, the real proofs of this, let me put it that way, it's much less pleasant. Okay, but that's all I want to say. Maybe you want to say something? No? Okay, good. So that's the final thing I want to talk about when I talk about types and temptations to cheat and reputation dynamics. Just to wrap up, we've seen there are good types, we'll see a bit more of them in a minute, which are good commitments. We've seen there are bad types that you want to separate out from, and these can impose costs. And we've seen and generate some nice dynamics. And we've seen how this temptation to cheat behind some noise also gives some interesting reputational dynamics. It's over to you guys now to find other kinds of dynamics in these models. Okay, so what I'm going to do now is I'm going to think about introducing long-run uninformed players. Okay, so in the world we were studying before, there was really no benefit to the short-run player to engage in any sort of experimentation. Experimentation today is costly. And you might learn something, but tomorrow you're dead because you're a short-run player. And when you have long-run players, that's not true anymore. They have an incentive to experiment, gather information, and learn about commitment types that may be in the world. And you can imagine the extreme reverse of this world, where we have a short-run informed player and a long-run uninformed player. And then we would be very much in the bandit model world. How would you learn about the types of your opponent? We're not going to go all that way today. What we're going to start off by thinking about is the case. It seems to have vanished off the top of the slide, maybe. Oh well. What we're going to start off thinking about is the case where delta 1 is going to get very big, the discount factor of the informed long-run player, and delta 2, the discount factor of the uninformed long-run player, is going to be less and fixed. Okay? And what are we going to show? Well, in that kind of world, very patient informed player, less patient uninformed player, we're going to see that reputations still exist, but they're typically weaker. However, you can use particular customized kinds of uncertainty to get very strong reputation results if you were so interested. And that's this point here. And these results, here's where I say it, are going to be true for the case when we're fixing a discount factor of the uninformed player and letting the informed player's discount factor tends to 1. Later on today, we're going to look at the case where both of those are equal and tend to 1, and then we're going to be in the world of repeated games of incompleted information where players are equally patient. And in that world, we get very weak reputation results, except for particular special cases, which I'll talk about, and actually relate back to our bad reputation model. Okay, so onward. So we're going to start with an example of discount factor of the informed player, small discount factor of the uninformed player. And we're going to give an example where reputation playoffs are lower. And then we're going to look at a result from Klaus Schmidt, which shows a particular class of games which are called games of conflicting interest, where the actual reputation bound is exactly the same when we have patient long-run players. And then we'll generalize that. And finally, we'll look at more complicated kinds of commitments in repeated games that you might want to think about. So here we have our good old battle of the sexes game. The red type is the commitment type. The green type is the normal payoff type. And in our previous world, if you think about George and Larry's lectures, you would look at this world and say, okay, the reputation bound here is 3. That's what you're going to get. What I'm going to show you now is that if we think about a world where the column player is more patient, it goes down. By just giving you an example. And the example is actually comes from the literature on repeated games with no discounting. But it works fine here. So here are the strategies. The normal type is going to play top until she sees a deviation from the column player. The column player is going to cycle. End periods, they're going to play best response and they get 3-1. And then every extra period, they play left and everyone gets nothing. And that goes on forever. 4 of that, 0 of that. 4 of that, 1 of that. 4 of that, 1 of that. If we observe a deviation, what happens is the normal type plays the stage game Nash equilibrium, 3/4, 1/4. And if we observe a deviation, if the row deviates, then again the column player plays 1/4, 3/4, stage game Nash forever. Okay? So we need to check that this is an equilibrium. And why? And the real puzzle here, I suppose, is the following question. Why does the column player not play the best response to get 3 every period? Why is it willing every nth period to get 0? And the answer to that is because they believe they will be punished if they don't carry out this pattern of behavior. And because they're patient, they care about this punishment. Question? No. Okay. So let's see how it works out. Well, here's the calculation. Let's think about the column player playing out this equilibrium in a period when they're supposed to play 0. They're supposed to get 0 today, and then if they keep playing out the equilibrium, they're going to get 1 less a little bit on in the future. And the little bit reflects the fact that every nth period they get nothing. How can you see that? Well, the easiest way of seeing that is let delta 2 tend to 1. If delta 2 tends to 1, this just tends to 1 on n, and so you get 1 minus 1 on n, reflecting the fact that every nth period you lose something. So that's what you get from playing out the equilibrium. What do you get if you deviate? Well, if you deviate, there are 2 things that could happen. You could be facing the commitment type, and then, well, who knows what you're going to get, but you could at least get 1 forever. So let's put the biggest thing you could get if you deviate against the commitment type. You get 1. And here, let's put the biggest thing you can get if you deviate against the normal type. Well, the normal type, you're going to deviate and you're going to get 1 today, because you're supposed to get 0. But then the normal type is going to punish you, and you're going to get 3/4 forevermore, because you're playing this stage game Nash equilibrium. So here we do the calculation, and you can see playing out the equilibrium is better than deviation if this condition down here is true and delta 2 is sufficiently large. Okay, so what's going on is that when the uninformed player is relatively patient, they don't necessarily pay a best response because they worry about what will happen if they deviate from some particular plan of responding to the commitment action. Okay? Any questions? Terrific. So, you might object to this. So let me play devil's advocate. Why might you object to this? Well, the argument goes as follows. The uninformed player plays as they do because they believe they'll be punished if they don't. Who does the punishment? The punishment is coming from the person trying to build the reputation in the first place. Why would they do this punishment? Why not keep pretending to be the commitment type? So those strategies I just told you are certainly a Nash equilibrium, but they're definitely not satisfying any sort of perfection requirement. So your first objection to what I should tell you is, but that's not credible behavior. That's not going to work. Well, I'm sorry for you, but actually you can rig it. So even and you'll see later how you rig it. Actually, you can rig it so that this is even subgame perfect equilibrium. No. Perfect Bayesian equilibrium. So credibility is not going to get you out of this. Okay? This is quite a general phenomenon. You see it in, and it first was noted by the Aumann, Hart, and those guys who studied repeated games without discounting and incomplete information. However, along comes Klaus Schmidt, and he noticed that in one particular circumstance, this argument doesn't work. In one particular class of games, you can restore the kind of reputation bounds that we saw when the short-run player was very, very short-run. And these are games called games of conflicting interests. So I begin by giving a definition of what a game of conflicting interests is. And that's a game where if you looked at all the commitments you could make, or Stackelberg commitments you can make, the best commitment you could make when your opponent plays a best response holds your opponent down to their min-max level. So an example of that would be an ultimatum game. What would be the best ultimatum to offer your opponent? The best ultimatum would be, you've got to give it to me all. What's the best response to that? Well, one best response is, sure, you can have it. And that gives the other person in the bargaining game their min-max level, 0. So that's a definition of that property. Let's define player 2's min-max level to be u bar 2. Let's think about the best possible commitment action for player 1. Let's suppose player 1 plays their best possible commitment action. Whatever player 2 does, they can get less than or equal to their min-max level against this commitment action. It says the commitment action is the action that min-maxes player 2. And here's an example of an ultimatum game. Here's an example of a game of conflicting interests. Here's an ultimatum game is another example of that. Any questions? Good. So, in this class of games, with long-run uninformed players, this result is true. And it says, for a small positive probability of the commitment type, for a fixed given discount factor of the uninformed player, if we can make the informed player sufficiently patient, then at every Nash equilibrium of that repeated game, the informed player gets something arbitrarily close to the usual reputation bound. We have to have an additional fudge factor in there, additional epsilon, just to deal with a long-run issue. But it's essentially the result you saw from Larry and from George. The difference here is delta 2 not 0 and this epsilon fudge factor. And it only works for one particular type, the Stackelberg type. So, any questions?
No, question here. So in general, delta 1 might have to be quite a bit bigger than delta 2. Can you say anything about when they might go to 1 at the same, more or less the same rate?
That's a very good question. I don't think we actually know the answer to that. Yes. Suppose, for example, we were to fix a factor that delta 2 was k times delta 1, and we let delta 1 tend to 1. Would it work in that case? No?
K times 1?
Sorry. If delta 2 tended to 1 as delta 1 tended to 1, but at a slower rate, would this result still apply? Is that the question? I don't know the answer. I know for sure that if delta 1 equals delta 2, it definitely doesn't apply. But no, otherwise, no. I don't know. Sorry. No one knows, I think. Maybe that's a big claim, but I don't think anyone knows. No. Good. So let's do the proof. So the proof is going to be very much like what you saw Larry's argument was, because it's quite an old paper, and the modern techniques that George was talking about just didn't exist then, I think. It's way back. So we're going to fix an equilibrium, and we're going to suppose the normal type mimics the commitment type. Okay, so if you remember Larry's talk, what does that tell you? Well, it says that if you behave in that way, there can be no more than a fixed number of periods, let's call it n zeta, where the uninformed player believes that the commitment action is being played with low probability. And what do I mean by low probability? I mean less than 1 minus zeta. So dependent upon how close we want the informed player to be to the commitment action, we can choose a number of periods, and these two things are linked, but the important factor is discount factor doesn't appear here. Okay, so that's what Larry showed you. And so what we're going to choose, first of all, is we're going to choose this zeta to be small so that the short-run best response to 1 minus zeta times the commitment action plus whatever else someone does is going to generate a best response to the commitment action. And then we're going to note something. And we're going to note the following argument. And first of all, let's suspend our disbelief and imagine that you knew you were playing the commitment action for the first n periods, and then maybe something else happened. Okay? How big can n be, and you know you're playing the commitment action for those first n periods? Well, you're going to get some reward after those n periods, but that reward is bounded by what appears in the game. You're going to play not a best response in the very first period, but thereafter the best you can get is your min-max payoff, because that's the definition of a game of conflicting interests. So if you're facing the commitment action, the best you can get is your min-max payoff. Okay? So this is a kind of an expected utility calculation under the assumption that you're not best responding to the commitment action in the first period, and after n periods, something happens. You get a reward. How big can n be? Well, if this was an equilibrium path, has got to be bigger than your min-max payoff. It's got to be bigger than u bar. So if I write the inequality, this is bigger than u bar, and rearrange it, I get this inequality, which is quite important. I'm sorry, it's way down there. And what that says is, you're going to make a finite loss now. You're going to have a long gain somewhere in the future. But you can't wait too long for that gain to occur. Because if you wait too long, this is going to shrink away to 0 and is going to be less than this. So what it means is, there's an upper bound on the number of periods in which you can believe the player is going to be close to the commitment action if you're not going to play a best response today. If you're going to play a best response today, that's fine. You can believe the commitment action is going to be paid forever. But if you're not going to play a best response today to the commitment action, you're going to lose a finite amount, and then you're going to have to believe that the commitment action is not going to be played n periods away. Okay? So we're going to combine that with our initial observation, that there can only be n zeta periods when the commitment action isn't being played with high probability. So this is my weird picture. So n means commitment action isn't being played or not being played with high probability. Here's where you might be best responding to the commitment action. Here's n period where commitment action isn't being played with high probability. Here where maybe where it is. We know there can only be n zeta of these big N periods. Oh, this is really bad. There's a big N there and a big N there. They're different big N's. I'm sorry. That big N means not commitment. That big N is the big N that came from the previous inequality. Sorry, guys. So we've got a finite number of times when the commitment action is being played. These finite number of times can be spread out, sure, over histories, but we can only allocate each of those to one block of n periods. Can't allocate each of these to any more than one block of n periods. So in total, how many periods can there be where we can justify not playing a best response to the commitment action? We can justify it in these, we can justify it in the next block, we can justify it in the next block, but after that, there are no more periods not best responding to the commitment type coming up, and so there can be no more periods where you're not getting the reputation payoff. So Klaus's clever argument used individual rationality to say you can't not best response to the commitment type very often. In fact, much more than very often, there's a finite number of periods, n times n zeta times, where you can't best response to the commitment action. But of course, now we're allowed player 1's discount factor 10 to 1, and so n times n zeta time periods of not best responding to commitment action don't matter very much in the great scheme of things, because I'm becoming more and more patient. Because I become more and more patient, I get my full reputation payoff after this phase has occurred. So that's Klaus's result. Now, could you generalize this to non-conflicting interest games? What's the general result when you have a fixed discount factor for player 2, let player 1's discount factor 10 to 1? Well, you can generalize it, and what you saw in that example I first gave you applies. That example relied on us punishing the player for not playing a best response to the commitment action. And thinking about what punishments we can apply generates a lower bound on the payoff that the uninformed player can get when they're responding to the commitment action. And that lower bound generates a set of payoffs the informed player can get when they're best responding to the commitment action. So how does it work without all that hand waving and blah blah? We first think about fixing a commitment action and allowing the uninformed player to play any action it wants to against it, provided an individual rationality constraint for the uninformed player is satisfied. And what's the individual rationality constraint for the uninformed player? Well, it's just coming up. You can get, if you deviate from best responding to commitment action, you can be punished and be held down to your min-max level. If you deviate, if you face the normal type. If you deviate from best responding to commitment action and you actually faced the commitment type, well then you can get your best response payoff forevermore. So best response payoff to the commitment type, min-max, weighted by your probability of the commitment type and normal type, defines another notion of individual rationality in this game, and this individual rationality constraint constrains what the uninformed player does when it faces the informed player. Okay? And so this is a weaker bound than the one we saw. It's not playing a best response, it's playing anything that gets the uninformed player at least this. And then, if you wanted to think about the reputation lower bound, we want to minimize player 1's payoff given player 2's payoffs satisfy this constraint. Okay? So those of you who know your undiscounted repeated game theory, this would be very familiar. Because these ideas and this kind of construction is what you see if you read Alman Hart or Forge or any of those people who wrote and Koren, Israeli, those guys who wrote on the equilibrium of undiscounted repeated games of one-sided incomplete information. This kind of construction is what you see. But that presents us with an interesting question, because in those games, players were equally patient, infinitely, but equally patient. Here, the discounted case, we're fixing the discount factor of player 2, letting the discount factor of player 1 tend to 1. So there's a lot of inequality in the discounting here, but the outcome kind of mirrors what we see in the undiscounted case with lots of equality in the discounting. So that's kind of a puzzle. So that's what I've just said, summarizing. This is a formal statement of that lower bound that I appeared on the bottom of that slide. This is making the point that this lower bound is like what you see in the limit of means or undiscounted world. And it seems like, I think something I read Alman said once, that in some sense, the equal discounting, you let the informed player move first somehow. I don't know what the intuition for that is, but it seems like that's what's going on. It's a puzzle. Any questions? Terrific. So we've seen now why introducing types of making players more patient might weaken reputation bounds. Okay? This is a lower bound on equilibrium payoffs. Now I'm going to give you question.
Well, just further to our discussion before about delta 2 and delta 1 going to 1.
Yeah.
I mean, if someone were able to fill in that gap, then the connection with the undiscounted case might be clearer.
Yes.
No.
Yes. I don't know. It feels like there ought to be another puzzle there, because if you find that this critical value of the ratio that looks like undiscounted, or maybe it depends. That critical value depends upon the amount of incomplete information. That would be very interesting too. Yeah. Yes.
I mean, we already know, even in the complete information case, that there are some discrepancies between the undiscounted case and the discounted
Yes.
case.
Yes.
You don't have to worry about dimensionality in the undiscounted case. So.
Yes.
Resolved.
But I want to come back to you then. Can I ask you a question? I wasn't there. But is there any relationship between the undiscounted case and the unequal discount factors, both discounted factors tending to 1, the Lehrer case? Because as I remember it, Lehrer did a paper with delta 1, delta 2 tending to 1, but at different rates. And he got a fatter set and different payoffs.
Yeah, I think it's
Okay.
I think that you get a difference.
Okay.
You actually get more. You get more payoffs with the unequal case.
Yes.
Than you do in the undiscounted.
But then you have a worry, right? If you have
Yes.
delta 1 and delta 2 tending to 1,
Right.
you've already got a bigger payoff set. So
That's true.
then the
That's
comparison is...
Yeah.
So maybe that would have been a good answer to your original question. I got there in the end. Yes, thank you. Okay, so where are we? So I was telling you that when we have patient, uninformed players, it looks like reputations might not be as good. But there's a counter-argument that says, maybe we're just choosing the wrong types. Maybe we should choose more complicated types to get ourselves better values to reputation. So the fact that player 2 is not best responding to the commitment action anymore may not be a problem if we choose a good commitment action, not just a stationary one. But then we have a follow-up problem. The follow-up problem is if player 2 is learning about a more complicated type, how do they know what that strategy is actually playing? You might be learning about a type who's actually playing tit for tat. But as you're just playing cooperate, 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 you just think that type plays cooperate. You never actually get to defect, and so you never actually get to observe the fact that it punishes you when you defect. Okay, it's a bandit problem. You have to be willing to take actions that may be short-run costly to you to learn about all the possible behaviors of a particular type out there in the world. And you may not want to do that for good reason. So when you introduce these more complicated types, the problem really is, how do you know what those types genuinely do? Or maybe you're just stuck at a self-confirming equilibrium. So there are two approaches. First approach, Chantal-Henri Freudenberg, Levine, and Pesendorfer, it's the thing that you should do. The thing you should do, introduce some noise. Make the uninformed players play in some noisy way. If they play in some noisy way, then they're going to do everything eventually. And if these commitment strategies are sufficiently simple, you'll eventually, just through the noise, learn what type is out there. And because of the noise, then our good old Freudenberg-Levine argument applies. We can get reputation bounds. So throw in some noise, get some nice lower bounds in when the commitment types are more complicated. Second observation, a much stronger observation, comes from Evans and Thomas. And they made the point that if you chose this hidden commitment type very, very carefully, you can choose it in a way that it educates the uninformed player. It gives the uninformed player incentives to learn about off-equilibrium path behavior. So how does the Evans and... So, okay, there's Chantal-Henri Freudenberg, Levine, and Pesendorfer. With those four authors, it ought to be a good paper, right? Look at that. Right. So in this... Okay, so as I said before, there are trembles in the uninformed player's behavior. This allows the uninformed player to learn all the behaviors, even off-equilibrium path behaviors of the commitment actions, and thereby we can use the usual reputation argument. That's one approach. The Evans and Thomas one, what you do is you choose the commitment strategy very carefully. And the way you do it is you, first of all, punish for... Okay, think about a particular game. You want to achieve this particular payoff in a game. You're the long run player, so you play the row, and you want to encourage the short run player to play this column. So we get this payoff. So I start off by playing this row. And as the column player deviates, I punish them. But this punishment isn't irrevocable. It lasts a short period of time, and then I go back to playing this row. If they deviate, I punish them again, a bit longer. And if they deviate, I punish them again, a bit longer. And I slowly ratchet up this punishment. And the way I slowly ratchet up is I give them long enough to learn that I'm this type. But at the same time, it ratchets up enough, quickly enough, so that eventually the short run player says, I'm not going to deviate from that action again. I'm going to get a really long punishment next time I deviate. And so they learn that they're going to be punished. They believe the type out there is going to be a type that's going to punish them longer and longer and longer. And therefore, they end up playing the exact column of the payoff matrix that the long run player wants them to do. And so it doesn't require noise. It's a very complicated construction, but it kind of exploits the fact that the short run player is not very short run, has some perspective on the future and the fact that they're going to get punished. And eventually, because they're going to get punished, choose to play the best response that the long run player wants them to play. Okay?
Sorry, but in this scenario, why would the short-run player not play exactly the right best response to a given state?
Well, there might be lots and lots and lots. It might be, for example, that we might be playing a game where I want you to play a payoff which gets you quite a low payoff. I'm doing really, really well. It's really bad for you. And so you might fight to try and get something else and think maybe there's another type out there. And so you might take quite a lot of persuading if this best response payoff for you, this particular action I want you to play, which isn't a best response, if that isn't very valuable to you. Okay. So, now we're going to look at the case where delta 1 is equal to delta 2, both of those are tending to 1. And generally in this world, we're not going to get a lot of reputation effects, apart from quite special cases. And I'll give you an argument which explains why that's true. A question?
So what is the result what's actually the result there?
For?
When the commitment type could be an automaton, could be something more involved?
I think...
It could be an automaton or something.
Yes, it is an automaton. It's a very complicated automaton. And I think you get the...
What can the
So,
player get?
do you remember the picture I showed you? No, probably not. I think you can get the biggest feasible and individually rational payoff to the informed player.
Right. Because you spoke in terms of a best response.
Yes, that I miss.
But that's not
No.
Could be better than that.
It could be much better than that. That's why I spit over there.
Okay.
You choose any response.
Any response.
Yes. Sorry.
Yeah. So you could actually get what you just said.
Yes.
Best payoff that is still, the only constraint is individual rationality.
Yes. And I think you need to be a little bit away from player 2's individual rationality, the fudge factor. So
Why do you call it an automaton?
it's a strategy.
It's a strategy.
Yeah.
It's strategy.
Yeah. Yeah, there was a time in people's lives when automaton were very popular, I think. Yeah.
It's a strategy.
And I think it was at that kind of period where it was a sexy word to put in the title. Not a...
No, because Martin was speaking in terms of some end period.
Yeah. Also, I did talk about end-person automaton, end-period automaton.
It should be
Yeah.
focused as well.
We shouldn't do this. George is still wedded to the automaton idea.
No. I didn't you see the restraint? I thought it was a very useful representation technique for repeated game strategy.
But they're real sods to draw in tech.
Not to be used here. There.
Okay, fine.
The word automaton implies a restriction on computing capacity.
Right.
Well, yes.
That's
Yes.
That's what the interesting thing arises.
Yes.
You'll have
here
some
there's
papers
not-
like
there's
Over
not-
and Elman a number of years ago.
I love that paper. Yeah. Yeah.
No, but here there's no restriction. Right?
Yes.
That's increasingly complicated.
Yeah.
Right.
Yeah. So, fine. Yes. So, we're agreed. So, anyway, we're looking at the equal discount factors, both discount factors taken to 1. And what I'm going to say now relates to that kind of topic. And I'm going to claim that we get weak reputation effects in that world. And I'll give you an example which shows you why that is the case. And then, if we have time, I will talk a bit about the exceptions. And why do we generally get weak reputations in this world? Well, what a reputation effect typically is about is introducing a small amount of uncertainty into a game. We're not talking about a lot of uncertainty, we're talking about a small amount of uncertainty. So one thing one could do is one could study the limiting set of equilibrium payoffs of the game. So the set of equilibrium payoffs as the discount factor tends to 1. In a complete information game, we know what that is, the Folk theorem results. What about in the incomplete information game? Well, that in general is quite a hard thing to find out. We have some papers on it, one by Marcin Pesky, for example. But one thing that's easier to prove than Marcin's results is what you might think of as a limiting continuity. And here's my picture to describe it. Here, this is a really bad picture, but along here we have how much uncertainty there is. This axis, complete information. And up this axis, we've got the equilibrium payoff set in the game. So complete information, equilibrium payoff set, and we're looking only at the limit as the discount factor tends to 1. Not on the way, the limit. And so this is the Folk theorem set, and there's a result which says that if you introduce a sufficiently small amount of uncertainty, the set of equilibrium payoffs as the discount factor tends to 1 is going to be arbitrarily close to the Folk theorem set in a very large class of games. So there's this continuity in the correspondence of equilibrium payoffs as the discount factor tends to 1. Okay? So that's like saying there are no reputation effects. Small amount of incomplete information, discount factor sufficiently big, no reputation. No restriction on the set of equilibrium payoffs. So, and I'm going to show you how you might prove such a result. And here's the game we're going to do it in. Almost the simplest possible game, a game of common interests. This is the common iterated dominant one. Sorry, it's getting late. I'm just telling you the blindingly obvious. Okay, we'll let discount factor be delta for both players. We'll introduce a type of uncertainty about the row player. We'll imagine at time t equals -1, the row player's type is selected, and with probability mu, they're a commitment type that always plays the top row. With probability 1 minus mu, their usual normal type, who has those payoffs in the matrix before. So that's stuff you know. I'm going to introduce a little bit more information because we have to deal with the minutiae of the equilibria. And the extra information I'm going to do is the aggregate strategy of the row player. With probability mu, they play action top for sure. With probability 1 minus mu, we don't know what they do. They have those payoffs. But we're going to call P1 minus P, they're mixing over the two rows. So I should have said that. And with pi, of course, then is the probability the uninformed player attaches to top being played. 1 minus pi the bottom. And the nice thing is, once we have pi here, Bayes' theorem is really easy because updated beliefs are just previous beliefs divided by the probability the commitment action was played. So that's Bayes' theorem. Okay? So a little bit of extra notation, but we're on our last half hour, we can do it. Okay. So how to build a bad equilibrium. Okay. And this is going to be nice and perfect and all the nice things you could want about an equilibrium, so it's none of this cheating with Nash equilibrium stuff. Question? No, okay. Go. Okay, so what we're going to do is we're going to build an equilibrium where you go through hell and then you get to heaven. Okay? And it works as follows. You're going to get lots and lots of periods of zeros, and then after that phase of zeros has occurred, then we get ones forever. And the way the period of zeros is going to arise is the following. We're going to have the column player play right, and we're going to have the row player randomizing somehow. And along the equilibrium path, they're going to do right, randomize, right, randomize, right, randomize for n periods, and then we're going to get ones forever. Now, of course, this randomization is going to require a kind of some tricky stuff with continuations to make sure indifference is there. But that's the general overview of what's going to happen. And if we have n periods of 0 and n periods of 1 thereafter, we're going to get payoff delta to the power n, and we're going to show that we can choose n so that as delta tends to 1, delta to the power n tends to 0 if mu is sufficiently small. So we're going to show we can make this payoff really, really small if mu is sufficiently small as delta tends to 1. So how are we going to do this? Well, let's imagine we're building the first period of this bad equilibrium. So that's what we're going to get today. The column player is going to play right, the row player is randomizing. And so now we need to be precise about continuation payoffs. What happens after tomorrow? Well, if the row played top, we're going to ignore the deviation from the column player to playing right. We're going to treat it like nothing has happened. And after these two events today, we're going to go to n-1 periods of 0 and then 1 thereafter. We're going to get delta n-1. So if reputations are preserved, we keep going. What happens if in the period when I played right, you revealed your type? Well, now we're going to have some indifference, because if you go up, you get 0 plus delta to the n-1. If you go down, you're getting 0 today, and so you're going to have to get delta to the n-1 tomorrow, just to keep indifference. So we're going to have delta to the n-1 after that one, delta to the n-1 after that one to keep indifference. So that's all the things we need for the equilibrium so far. The issue, though, is why is the column player playing right? How do we give the column player incentives to keep away from best responding to the reputation? That was something we talked about before. And how are we going to give these incentives? Well, it's going to come from this randomization. The only continuation payoff we haven't filled in is after this one here. After this one here, we're going to have to make life miserable for, well, the column player. Because we're going to make the column player get punished only in this event. What has happened in this event is the column player cheated and did something they shouldn't do, but simultaneously the row player revealed their type, and now we're in a complete information game and I give them whatever I want to give them. So what shall I give them? Well, there's the question marks. What shall I give them? Let's give them nothing. That's the worst I could give them. We'll give them nothing. So these are now a complete description of the continuation payoffs in this game and a guess about the equilibrium actions. So all we need to do now is check that this is equilibrium behavior in this period. And so the thing we've rigged it so this player's indifferent. We just need to check this person wants to play right rather than left. So let's check that. If you play right, you get 0 today for sure, and then delta discounted delta n-1, you're going to get delta to the power n. What about if you play left? Well, if you got lucky and the other guy played top, you're not going to get punished. You're going to get 1 today and then delta to the n from the future. If you were unlucky and they played down at the same instant as you played left, you're going to get nothing. Okay, so the incentive constraint is this. The probability that top was played times nice stuff, probability that bottom was played times nasty stuff. That's got to be worse than playing out the equilibrium, which gives us this inequality on pi. Not surprisingly, you've got to play down with high enough probability so that the punishment bites. You can only punish when you play down, so that's got to be a big probability event. It can't be too small. But, now this is the difference from what we saw in bad reputation. There's deltas in here. It's like there's gold in them there hills. There's deltas in here. So the deltas tend to 1. This stuff is converging to 0. So that means you don't have to play down with very high probability to discourage this deviation. So why is that helping us? Well, what's that going to do? It's going to give us, as delta tends to 1, lots and lots of periods in which down can be played for a given amount of probability of the commitment type. The total probability down can be played is bounded above by how much commitment type probability you've got. If you haven't got much probability of the commitment type, you can't have down played in many periods. If you can have down played in lots of periods. And the discount factor tends to 1, more and more periods. So let's just go through the calculation. And we have to bring in Bayes' theorem now, right? Because playing down, Bayes' theorem applies and you get some updating of beliefs. And so here's the Bayesian update. here's our condition on pi, and now we want to ask how many periods can we play down? So how many periods can we play down? We can play down for n many periods as long as this number is bigger than that number. Okay? So as this gets smaller, probability of the commitment type gets smaller, we can have more n's. So here's a picture of what I've shown you. We can have no periods of hell and no constraints on the set of equilibrium. We can have one period of hell, and then we have not too high probability of the commitment type. 2 periods, lower probability of the commitment type. 3 periods, 4 periods, 5 periods, so on, so on, so on. These are the equilibria we've just traced out. So the question now is a limiting question. What does this object look like as delta tends to 1? And that's a really easy calculation to do. Here's this bound. Here's a very obvious piece of algebra which we put in there. And we solve, and we find that delta to the power 1 over n has to equal this object at that bound. And it's not very difficult to see that as mu tends to 0, that tends to 0. So what we've shown is that as the discount factor tends to 1, and as the players become more and more certain, or that the normal type is present but not absolutely certain that the commitment type is present, we can get equilibrium payoffs, delta to the power n, arbitrarily close to 0. That's the continuity result I told you about. Any questions? Okay. Yes, good.
Maybe I missed the point. So why do you construct this back equilibrium? What's the message?
Why? The message, that's a very good question. I'm glad you asked me that. The message is reputation effects generally are non-existent when they have equal discount factors. We've got a small amount of uncertainty, and there is no equilibrium. There is an equilibrium payoff arbitrarily close to 0 in this game, as the discount factor tends to 1.
Feels like I missed something quite central to all this.
Oh dear, sorry.
Player one plays right because he's afraid of the punch.
That's
How do I get player 2 to punch? What?
player 2's not punishing. Player 2 is being punished.
Sorry. How do I get player 1 to punch?
Ah,
Player 2 plays right because he's afraid of the punishment.
right. Well, player 1, equilibrium randomizes, right? Simultaneously. So if the deviation occurs at the same time as I revealed my type, we're in a game of complete information. I can choose any continuation equilibrium of that game I want. I made a good choice. I chose 0, 0. If I could make a bad choice and this result wouldn't work. Yeah. But it's a funny kind of punishment mechanism. That if you deviate and then I have to punish you, it won't work. But if you deviate and I punish you at the same time, it does work. So actually, but that's a very good point you make. So I hope I'm going to get to that in a couple of slides again. So let's see. So the key feature here is that we're getting as you've pointed out, we're getting the uninformed player not to play a best response to the commitment action, and that not a best response was being played many, many periods as the discount factor tended to 1. Think about that and compare that with the bad reputations model. In the bad reputations model, whatever the discount factor was doing, if we started off at this particular belief, there were a fixed number of periods where we ended up at the equilibrium where payoffs were 0. What's going on in this world, in some sense, is that the steps are shrinking as the discount factor tends to 1. And so it's taking longer and longer and longer to get to where we're going to settle down. And this time taken to settle down has a big effect on the payoffs, because we are discounting. So discounting averages what happens in the short run with what you get in the long run. Okay. So I've said all this. There's something subtle going on, which you may have missed, but so I'm going to emphasize. The subtle thing is, as discount factor is tending to 1, the probability of being punished in any one period is shrinking and shrinking and shrinking. So you're playing down with smaller and smaller probability. And the reason you can get away with that is because you're becoming more patient. So a smaller probability of an even bigger loss is still enough of a punishment. So I said, apart from special cases, this holds true. So what are the special cases where it doesn't hold true? Well, there's a paper by Jimmy Chan who looked at a world where the commitment action is a strictly dominant action in the repeated game. So it's kind of hard to imagine. I'm sure you can imagine a game where there's a row which strictly dominates every other row. And if that was the case and there was a commitment type that played that row, then the argument I just give you wouldn't apply. There's a paper by Eddie, Wolfgang and I where we looked at games of strictly conflicting interest, not just regular conflicting interests, where this argument doesn't apply. Why? Well, it's easiest to go back and look at that picture again where I put the zeros in. Here. Okay? The reason the zeros work is that they're a long way from these numbers. So you can make a small probability of a big loss. And that's an effective punishment. And you can get lots and lots of periods of not best responding as a result of that. If these payoffs are quite close to these payoffs, order 1 minus delta away from them, not going to work. You can't have a very small probability of this kind of a small punishment and get this argument to work. If these numbers are close to these numbers, you have to have big punishments and big probabilities of playing down. And you can only have a finite and bounded number of big probabilities of playing down. So it doesn't work in that world. Question?
Sorry, I missed something in your construction of that.
Mm-hmm.
Why does you're saying that the normal time randomized?
Yep.
Why do you randomize?
Because he's indifferent.
Why is he indifferent? I mean, the
He's
other
going to
guy
get
from
dealt.
time to time plays to the left.
No. On the equilibrium path, the other player plays right. Our constraint is we want to stop them playing left. If they deviated to left and the down action was being played at the same time as the deviation occurred, that's what we're concerning ourselves with. But on the equilibrium path, they should be doing this.
So you get what are the set of equilibrium paths you get?
In this game,
Yeah.
it's actually given by that found. Yeah,
Okay.
it converges to the folk theorem.
So the idea is that you set the periods in which this guy plays right,
Yes.
and then there are other periods in which he...
After that, it's
If he deviates, then you... Okay.
yes. Yes, very good. So that's another reason why this construction might work, and that was a very small class of games. Mehmet Ekmeki and Alpatakan have some other papers where they have another construction where this number has to be kind of close to this number for a different reason, due to the shape of the feasible set. And if this number is kind of close to this number, order of 1 minus delta away from this number, then again, this construction doesn't work and you get these very strong reputation results. Finally, and I've got nothing left to say after that, Johannes said I ought to teach Abra Pistachetti, but
You've got time.
no. I don't have slides.
Maybe I'm getting tired also. That what role did the discount, the fact that the discount factor, I mean, this result is when those two discount factors go together.
Yes.
Why doesn't this argument apply if the informed player is more patient? It seems.
So if the informed player is more patient, well, what happens is the n you get out of this calculation is determined by the uninformed player. So we're going to get a number of periods in which you can't best respond to the commitment type determined by the uninformed player's discount factor. It's fixed. Push the informed player's discount factor to 1, they get 1.
I mean, the idea is that the uninformed guy plays the right column, and sometimes, I mean, you get the folk theorem, right? They're having the uninformed guy play right in a certain proportion of the periods and plays left, and if he deviates, then, there's a chance the 0-0 would be revealed, and then he would move to 0-0.
Yes.
What role does the fact that the two discount factors go to 1 together play here? That's what I'm
okay.
missing. I mean, same argument seems to apply also if the informed guy is more patient.
So if the informed guy, so let's fix the uninformed guy's discount factor.
Yeah, but I guess the question is related to Eric's, which is if they're asymmetric but they both go to 1.
Yes. That maybe that. Oh, sorry. I was thinking fix delta 2, let delta 1 tend to. No. So I agree. I've never looked
Delta 1 go to 1, but
at the different rates.
Delta 1 goes to 1 more quickly.
Great question. No one's ever bothered. I don't know why. It's a great question. Yeah. I think it would.
So it's not specific to the fact that
No. But we have a different discount payoff set.
I thought you were making a point that it makes a difference that whether they go together or not.
No. I'm making the point.
Whether one goes to 1 and the other is fixed.
Yeah. So we were doing delta 2 fixed, delta 1 tend to 1.
Strictly speaking, we proved it for the case where the two deltas
Yeah.
are equal.
Yeah. But it might well work for different.
Yeah, it might work with different deltas, which both go.
Right.
Yeah. But of course the payoff set will be different, right? Because it'll be fat. It'll be kind of bowed out. So yeah, there's something else going on, but I don't know. But yeah, no. Where were we? Wrapping up. Final 2 points. Okay. We're looking at cases where this argument doesn't apply, and you alluded to it. You did. You're hiding now. When there's an order to the moves, when they can't move simultaneously. If there's an order, and in particular if the commitment type moves first, these arguments don't apply. And there are some nice results that if the commitment type moves first, then very strong very strong reputation results, even if the players have equal discount factors. And that's quite interesting. That's a paper by Mehmet. Final point is to do with imperfect monitoring. It seems like if there's imperfect monitoring, this kind of construction won't work as well. Why? Well, what we're relying on here is a very, very small probability of down being played. When you have imperfect monitoring, the very, very small probability of down being played gets kind of swamped in the noise in the monitoring technology. And because it kind of gets swamped by the noise in the monitoring technology, you don't learn very much when you see the down signal. You might revise your beliefs downwards a little bit, but not very much. And because you've revised your beliefs down a little bit, you're not going all the way to the complete information game as a result of down being played once. You're going to a little less faith in the commitment type. So in games with imperfect monitoring of the row player's actions, it also looks like this construction doesn't work, and the only equilibria give full payoff 1 to the row player. Now, I'm sorry for finishing early, but I really have nothing else to say. So,
No one is going to complain.
so that's the very last slide on my talk, and that's actually what I just referred to. Thank you.